Time doesn't only tick, it stretches, stutters, and sometimes cheats our expectations. Today we'll trace how technology, travel, and memory bend our sense of time, because physics sets the rules while biology and culture rewrite the script. The core idea is plain. Clocks are agreements with the world, which meant when the world changes speed, altitude, or routine, our agreements need help. Start with the clock that hides in your pocket and whispers to space. Your phone asks satellites for its position, and that position depends on timing measured to billionths of a second. GPS works by comparing how long radio signals take to reach you from several satellites. If the satellite's clocks drift, your location drifts, therefore timing errors turn into distance errors. Einstein predicted 2 ways for clocks to misbehave. Moving clocks tick slower, and clocks deeper in gravity tick slower. That's speed time dilation and gravitational time dilation in one sentence. GPS satellites orbit around 20,000 kilometers above Earth at roughly 4 kilometers per second. Up there, gravity is weaker than at sea level, which meant their clocks would run faster because of gravity but slower because of speed. The two effects don't cancel, they add to a net offset. The weaker gravity speeds them up more than motion slows them down. So without correction, satellite clocks would race ahead by about 38 microseconds per day. That number sounds tiny, but light travels about 300 meters in a microsecond. Therefore, 38 microseconds would push your position wrong by kilometers each day. Engineers handle it in 2 ways. They tune the satellite clocks before launch to tick slightly slow on the ground, which meant once in orbit they match Earth time on average. They also apply continuous corrections from the ground segment. Tiny changes in orbit, temperature, and even Earth's lumpy gravity require updates. Therefore, the system keeps time aligned so maps don't lie. This is relativity as infrastructure, not philosophy. If a teenager in 1997 used a car navigation unit, that route depended on 20th century physics, and every rideshare today still does. Next, let's travel with a body that keeps its own time. Jet lag is the mismatch between your internal clock and the local time after crossing time zones, because your circadian rhythm changes slowly. Fly from New York to Paris and jump 6 zones, your body expects midnight when the city serves breakfast, which meant sleep, mood, and appetite fall out of tune. Social jet lag is the same mismatch without planes. Your weekend schedule drifts from your weekday schedule. A student sleeps from 1 a.m. to 9 a.m. on weekends but 11 p.m. to 7 a.m. on weekdays. That 2-hour swing acts like flying 2 zones every Friday and returning every Monday. Therefore, Monday feels rough even without a boarding pass. Simple tactics help, not miracles. Shift your sleep and meals toward the destination a day or 2 before travel, because small nudges add up. Use light as medicine. Morning light at your new location pulls your clock earlier, while bright evening light pushes it later, which meant timing light exposure matters more than melatonin alone. Keep wake-up time stable and walk outside after landing. Short naps under 30 minutes can refresh without stealing night sleep, therefore you recover faster. Hydrate, avoid heavy late meals, and limit caffeine after local noon. These aren't cure-alls, but they reduce friction while your internal clock negotiates a truce. Now to the strangest stretch of all. Time speeding up with age. Many people report that summers at 8 felt endless while adult years vanish, because our brains compress familiar experiences. A quick definition: memory compression means we store fewer distinct markers when days repeat. Routine produces fewer index cards, which meant looking back reveals a thin stack and feels short. Novelty slows perceived time in the moment. First days at a new job, first visits to a city, or learning a skill flood the brain with details. Therefore, the memory becomes dense and the week feels longer in hindsight. Proportion matters too. 1 year is 1/8 of an 8-year-old's life, but only 1/40th at 40, which meant each year feels smaller as a slice of your personal timeline. We can't halt the ratio, but we can seed novelty. Schedule deliberate firsts, new routes, recipes, or languages, because fresh cues widen the memory log and stretch subjective time without adding minutes. Finally, let's separate 2 fixes people often blend: leap years and leap seconds. They sound alike but solve different problems, and the evidence for each lives in astronomy. A leap year corrects the fact that Earth orbits the Sun in about 365.142 days, not a neat 365. The Gregorian reform in 1582 added a rule: years divisible by 4 gain February 29th, except century years unless divisible by 400. Therefore, 2000 was a leap year, but 1900 was not. This keeps calendars tied to seasons, so March still welcomes spring in the northern hemisphere. It's a slow, predictable correction, which meant we can publish leap years centuries ahead. A leap second fixes Earth's wobbly rotation. Tides, winds, and the planet's core make length of day drift. Therefore, atomic time outruns or lags the sun by fractions of a second. Since 1972, timekeepers have occasionally added a second at the end of June or December. That keeps everyday civil time within a second of solar time, which meant clocks match the sky for navigation and astronomy. Leap seconds bring headaches to computers and networks. Some systems stumble when the same timestamp repeats. Therefore, engineers must smooth or smear the extra second when it appears. So leap years align calendars with the orbit. Leap seconds align clocks with Earth's spin, and the two adjustments march to different drummers. All this bending of time, relativity in orbit, circadian drift across rooms and continents, memory compression across decades, and calendar patches across centuries, lands us at a navigational puzzle to close. You have a same-day meeting scheduled at 3 p.m. local time in a Pacific city. You can choose a flight plan that crosses the international dateline eastward or westward because routes exist in both directions. One direction risks arriving one calendar day earlier than your takeoff date. The other risks arriving one calendar day later, therefore your calendar can betray your intuition even when the flight lasts the same number of hours. Your decision scenario is this. Pick a direction, east across the line or west across the line, and defend in one sentence which way flips the calendar backward and which way pushes it forward. Be precise about earlier versus later and anchor to a simple example if you like. We'll reveal it and highlight the best takes in the next MindMaze stream. Here's the distilled takeaway. Time isn't just what clocks say. It's what gravity, motion, habits, and history do to those clocks, which meant good timing demands good models. If this episode helped you see when seconds slip and days deform, subscribe for more mind-stretching journeys each week.